thank you very much for being here, and thank you for being patient. Let's see. Let me introduce myself. My name is Sara. I am a backend engineer in DAZN, a global platform that streams sports events. Who has ever heard about DAZN until now? We have one. Well, the product has not yet launched in the UK, so that makes sense. Our backend services are powered by microservices, and we follow a serverless first approach. Today, I am not going to talk to you about the successes that my team experienced or how performant we made that particular service. Today, I'm going to talk to you about failures and how important they are and the learnings that my team achieved with these failures. So, how many times have you heard somebody from your friends or colleagues saying, "Oh, I love serverless. It's just so easy. It's so simple. AWS takes care of everything for me. I love it." Maybe you as well thought about it the same. And indeed, in certain scenarios, that's the case. That's true. So for instance, let's assume that I have the task as a backend engineer of building a simple REST API endpoint that needs to be available and scalable. So assuming that serverless wouldn't be an option, then what I would do, I would have to provision a number of services. Like, for instance, I would have to provision a load balancer. I would have to provision a set of EC2 instances distributed across at least 2 availability zones. For those of you who are not familiar with the AWS infrastructure, let's see. Yeah. So the big uCentral1 box represents an AWS region, which is a big data center, which is in Frankfurt, located geographically. The smaller boxes, they represent satellite data centers, and those are the availability zones. In order for my system to be available, I needed to be also geographically distributed. So that's why redundancy of computing units is necessary to make my system available and resilient. So again, if I have to build this without serverless, I would have to provision, as a backend engineer, a Route 53 records, then an application load balancer, EC2 instances on multiple availability zones. And then I have to create an ECS service with multiple tasks. I have to set up VPC, subnets, auto-scaling, and probably I forgot about something. Well, that's a lot. That's a lot. With serverless, I can create a set of Route 53 records. I create one API gateway with one Lambda, and what's great is that my service is already distributed, available across all the availability zones of that particular region. And sometimes people don't even know about it. I think as a backend engineer, you should know about this. But what's cool is that you don't need to worry about it, because all the circuit breaking and reliability measures that normally you would have to set up yourself, those are those are managed by AWS itself. So when a request comes in, the request goes to the availability zone that it's the closest or healthy as well. So availability zones that are not healthy are also excluded by AWS, and I don't have to worry. On top of that, containers, security, are all taken care by AWS itself in the Lambda. So I just have to provide my code runner, my function, and that's done. I can focus on the business logic without the need to worry about all these things. And if you need a data storage, like in the case of a DynamoDB table, then also that it's also synced, the data is synced to the other availability zone eventually. So that's great because it's a real pain as a backend engineer to make sure that your data is globally available and in sync. So until now, it seems like serverless might be the answer to all my needs. But is it really the case for all the scenarios? So let's take as an example two microservices. I will go over some details, but just to get you the gist. I have a simple REST API that is public-facing. It's behind WAF protection, so Web Application Firewall. That means that I control the access. I have an API gateway, which is an HTTP proxy that takes an HTTP request from the internet and transforms it into an event, a format that the Lambda, my computing unit, can understand. I protect this HTTP endpoint behind a Lambda authorizer, which is in charge of making sure, OK, you, client, you can pass. You are authorized to use my computing unit. So this Lambda takes a post request, it validates it, and if the request is successful, then sends an asynchronous invocation to another microservice, which is in charge of getting that information from the previous Lambda and generate some entities based on the data that the Lambda received. In case of asynchronous invocations, the first Lambda just sends a message to the other one, say, OK, I need this. Can you give it to me? And then doesn't need to know anything about it, because then the second flow is completely encapsulated and asynchronous. And in the case of the second microservice, after the Lambda generates all the items that I need, a notification is sent. Whether this is a failure or a success, the notification needs to be sent. And if something goes wrong, you can set up a dead letter queue, which means that here I put something, the messages that the Lambda were not able to process. So far, so good. When we implemented this, we thought it was a good solution. However, after implementing these locally and on our dev environment, we started deploying this, promoting this architecture to stage and production as a dark deployment. We weren't live, but promote. So yeah, what happened is we start noticing an abnormal number of errors, just Lambda errors. And what we figure out is that the granularity of the metrics, the CloudWatch metrics in the Lambda, were not really helping us understanding what was the cause of those problems. So we had to log in we had to go in our centralized login and see, oh, there is a Lambda timeout. Why are we getting so many timeouts? Well, the answer was that because we were using the dev environment so often, the Lambda was always warm, so we didn't notice the problematic of this particular scenario, that every time that this Lambda was cold, it was always cold. And in this particular scenario, this was an internal tooling, so the Lambda would eventually be most of the time cold because we don't have user traffic. We don't have production traffic. So that was one problem. In case of failure, the standard behavior in case of asynchronous invocation is that the message that is received and is failing is retried 3 times. This is not something that you can change. And another problem arises, which is Lambda and serverless is a very flexible solution, However, there are some hard limitations. In this case, we encounter a problem when business or the product team came to us and we were like, okay, now you are generating X amount of items in this Lambda generator, but in the future we want to generate this time 10. And because the execution time of the Lambda was proportionate to the number of items that were to be generated, this is not really easy to implement because the time limit was met. So what can you do here? We thought about different possible solutions. One way would be to use step functions. So you could divide the computing units into different step functions and have like orchestrated, and have like a shared state, which would be the entities. But we figured that that would be maybe not the easiest. It was harder for us. For us, it was an overkill. So what we went for in this particular case is to have an SQS in the middle as a proxy that would give us more power in terms of retry policies and delays and concurrency. Have one ECS poller, a long poller, that would get the message. And in case of failure, they would send a message to the stakeholders. So for us, this was the simplest solution. So we talked about asynchronous invocation, but there is also another case about event source mapping. So to explain a bit this diagram, we have another HTTP endpoint that is taking requests and forwarding them to an application load balancer, which is integrated with an ECS service, which takes data, reads data, or writes data to a global DynamoDB table. Why is global? Because this particular service was user-facing, so not front-end facing, but was getting user data. And because we have stream sport events, we have the additional challenge of having a lot of traffic at spikes. So in that case, Lambda was not as performant as an ECS service, so we had more granularity over autoscaling. And we deployed this on 4 different regions for availability and resiliency as well. So we have this HTTP endpoint. And then we also had this requirement of reporting any information that was changed into this DynamoDB table to our data team for their own metrics, to study, to see, well, how can we use them for our own business decisions. So we had to implemented an event source mapping, which means that every change that is applied to any record of DynamoDB then is transformed into a streams of records, events, that is consumed by the Lambda, that you can see the data processing Lambda. And this Lambda then parses it and then puts it in a S3 bucket via Firehose. And so far, so good. Until not. So even in this case, the service was not really live, so we were able to capture this problematic before going live. What we noticed is that at a certain point, we stopped receiving data in the S3 bucket. And because we have our observability in place and metrics, we were notified about it. And we were notified also about the fact that the Lambda was returning a lot of errors. So we log into the Lambda, in the logs of the Lambda. And what we noticed is that we recently, before this error occurred, we added another column to the DynamoDB record. We updated the ECS to comply to this new value. We updated the Lambda to accept this new value, but we weren't defensive enough in the way we were validating that information in the ECS. and we forgot to update our integration test. So we weren't sending this value in the integration test. That means that that value was not persisted in DynamoDB, and that means that the Lambda was expecting this value to be filled, but it was not. And we didn't capture this. And what happened is that we went to see how is the Lambda, so how is this event source mapping configured. We trusted AWS with the default settings to see, OK, if in case something happens, we trust you. And what we saw is that we missed to see that there was a very important setting, which is how to handle in case of failures. And we also noticed that by default, if something happens, the message that was failing will be retried for 10,000 times and then expires. What that means, it means that in case there is one error, if you keep the default settings, the event will keep on being retried with exponential backoff. So the more tries, the more retries, the more longer is the waiting time until the next retry. So this event will be retried until it's succeeding, until expires, which by default is 24 hours, and all the max retry limit is reached. And this event will clog the whole stream, and the new events that are coming will not be processed until this event will succeed. I mean, this is a problem because this blocks the whole flow for a long time. And one of the metrics that I recommend to check out is the max iteration age. So we were really surprised to see these default settings, and it was really a discovery for us. So let's move to the next case. We had another REST API endpoint in another microservice. In this case, also an application load balancer, with ECS, that is getting data, reading data from a global DynamoDB table. And there was another ECS service from another microservice which was in charge of populating the global DynamoDB table. So we had on one side access from multiple regions from all over the world, so read operations, and on the other side, a lot of write operation over the same global DynamoDB table. Everything was OK. And in this particular case, we didn't really have any failure or problem bug that was hosting that, but we digged a bit more into this scenario. And what we found is that looking at the logs, we were seeing a lot of logs coming in. They were detailing how the data that we were expected to have was changing because there was a failure happening while talking to the DynamoDB table or writing to the DynamoDB table. So we did some digging. So we went to the Amazon DynamoDB documentation to see, OK, how does this work? Like, let's learn a bit more. And you would expect that something like failure modes or errors is something like more in your face in terms of, especially if you claim that the service should be resilient as available, it's important that you know how can it fail and what should I do to prevent it to fail. But it took us some time to find the failure modes for DynamoDB in the documentation itself. And as you can see, it's really a nested voice into the sidebar. So that was really, really interesting. And this is a very compressed page and represents all the possible errors that DynamoDB can give back to you when you use the SDK or when you invoke DynamoDB to write or read. And why is this important? It's important because not all of them should be retried. Some of them, yes, you should retry, but some of them no. So it's very important that you're aware of this. And we were lucky enough that we were relying on the AWS SDK. And what we figured, like looking at the AWS SDK for Node.js, we figured that under the hood, we didn't really know about it, but under the hood, the AWS SDK was using HTTP as a protocol to connect and talk to DynamoDB and to do the right operation. And we figured out that actually that happens for all the AWS serverless services. So every time they use the AWS SDK, under the hood, an HTTP call is performed. And the benefit of the SDK is that there is a wrapper around all sort of retry strategies and policy that the SDK is managing for you. I've seen around sometimes that some people prefer to not use the SDK, or maybe they want to connect using their own like HTTP, custom HTTP headers. I've seen it. I would say be aware of this because, I mean, you have to handle all of this if you decide to do that. Also, so yeah, so as I said, the operation is done via HTTP, and we were lucky enough by using AWS SDK. So be careful about it. Another interesting failure mode is something that we figured out doing load testing. Also, this service was not on production yet, so we were load testing before the actual release. We have another REST API endpoint or set of endpoints behind WAF, Web Application Firewall. In this case, the API gateway is integrated with a network load balancer, which operates on a TCP layer. So the application load balancer operates on an application HTTP layer that has more granularity over the routing. The network load balancer operates on a level underneath, which is a bit more performant. The network load balancer is then integrated with an ECS service. So we were running this load test. I think it was 7,000 requests per second. And that's very far from what we have as a worst case scenario. And what we kind of figure out, because we have our observability in place, we have our dashboard, we have our monitors, our metrics, we figured that we were getting some 500 errors from the API gateway. And that was interesting. And we're like, OK, what it is? To be fair, those 500 errors, not 500, 5x6, because in the metrics from API gateway, you don't have the granularity of the status code, unfortunately. You only know that it's a 5x6. So it could be 500, 501, whatever. So you don't know. So we were like, OK, let's check in the logs. The first thing we did was to go into the logs of the ECS service and the metrics of the ECS service, because we had metrics in place both for the API gateway and the network load balancer and the ECS. So we started with ECS, and ECS seems fine. So we are not getting anything. That means that the problem was before. So what we did, we checked the logs from the API gateway, and we found out that there was this weird error, which is execution failed due to network error communicating with endpoint. Luckily for us, that was not severe enough to be a big problem, because this error was happening consistently, but only for 0.0007% of the request, more or less, which is in compliance with our availability requirements, SLOs. But still, it was very interesting. So we raised a ticket in the AWS support and asking, why is this happening? And as they explained, and I have to say, the person from the AWS support gave an explanation that was very, very interesting, and I learned a lot. So what happened is that this can happen for multiple reasons. When you create a network load balancer, it's created inside an availability zone, and because our service, ECS services, was distributed among different availability zones, there can be a network issue while communicating with different availability zones, or like the ECS tasks. And because of that, the API gateway was not able to, basically getting a 504. And that, the idea that an API gateway or an AWS service can fail never even occurred to me. But this is actually true, because no service is perfect. No service is 100% reliable. And if you go to the documentation, you will see another hidden page, which is related to all the AWS services, service level agreement. So what can you expect in terms of availability and reliability on any AWS service? And what we figure, for instance, is that API gateway is extremely available, highly available. So for 99.95% of the requests, you can expect it to be up. But the application load balancer, for instance, was slightly more available. So I think 0.05%. That was very interesting for me, because the choices of services so the service that you choose to support as an underlying infrastructure, it's also based on the availability requirements of your service. So if you need a service that is very, very, very as available as possible, that means the API gateway would not be the best choice, maybe, because API gateway has a certain percentage, but so does every single service that is in the chain. ECS, network load balancer, my own service can fail, like my own code can fail. So you need to take that into account if your standards of availability are very high, so they are in the zone. So that was a good learning. And if you go to the API gateway documentation in terms of error handling, you will see that they tell you exactly what I said here. So we can fail. We are not perfect. And that means that you have to be prepared for this. That means that if you get a certain status code from us, according to your service and according to the status code, you must or must not have a retry policy or strategy in place. And that means that if I manage a REST API, a service that has a REST API endpoint, I need to talk to my consumers. It can be either the front-end team or another backend service that consumes my endpoint, API endpoint. Listen, we gotta make sure that you got all the retry policy in place if it's not enforced in your company. So what did we learn? We learned that you cannot have a resilient service if you have not your observability patterns in place. A system cannot be resilient if you don't know what's going on. If you want to automate error handling, you need to have the data available so that your system can react to it. And resiliency patterns means login, metrics, custom metrics, alerts, monitors, health checks. You can't tell that your system is resilient if it's not observable. So observability is paramount. The benefit of serverless is that I, as an engineer, can focus on business logic, and I can trust AWS or any cloud provider to take care of certain boring and very not so nice tasks like security or operating system, containers orchestration. But when you do that, you also lose control over how granular your resiliency patterns can be. So if you want to have more control, there is a trade-off. Another learning, and this is something that I say every week, basically, together with my team, is that I spend, I think, 10% of my writing, like code programming, writing business logic, and 90% writing tests. Why is that? Because writing tests for code that is supposed to run in distributed system, it's tough. Because when you have distributed systems, you have to handle failures that can happen in your upstream or downstream dependency. So if I'm talking to Dynamo, if I'm talking to another backend service, if I'm talking to Salesforce or another web service, I need to, if I want my system to be resilient, I need to take care of failure handling in my business logic. So even the retry policy per se, unless it's inside the library, but if I want something custom, I need to be able to test it. I want to make sure that if something fails, maybe my metric provider is sending the metrics to whatever, Datadog or New Relic. So in order to achieve that, you need to set up mocks, stubs. So the testing can be a bit painful sometimes. And that's inevitable when working with distributed system and microservices. As we learned, default settings are not always optimal. There was something that it's a learning. So what I do, since I think that happened like 1 year ago or something, I always go to check, okay, what are the failure modes, what can go wrong? That's very important when you start working with a service that you don't know yet. You need to go and say, okay, I want to know what's going wrong, what can potentially go wrong? I want to establish what's the level of severity, how can my system react to these problems, or how can I automate the failure handling? So you need to know before starting working with a service what can go wrong. And distrust default settings. Another learning is you need to have retry policies set up. In case of AWS SDK, that is taken care for you. Otherwise, you need to do it, and that's a must in distributed system. As we learn looking at the API Gateway service level agreements, nothing is perfect. Nothing is 100% reliable. Everything can fail, and that's OK. It's impossible to have something that is always up. But you need to be mindful about the services that you choose and their reliability to make sure that your requirements are met. And to conclude, failures cannot be avoided, but resiliency means that you are prepared for it and you can automate it. Thank you.